Hey guys, I just wanted to make this quick review video for you going over some of the topics for exam 3. I know Anna and Tim are going to do these too, and we kind of split up the material. So today I'm going to be talking to you guys about the big picture of metabolism, just going over that very briefly because Tim's going to go more in depth, I think. And then we're going to talk about muscle contraction, some random things that I thought would be good for you guys to know, about like alpha helixes and beta turns and stuff. So we're gonna get started here, and I'm just gonna show you guys my notes that I think are really important. Here's what I took notes for the big picture. So we know with metabolism, we put things into our body and the end goal is to get ATP out, because ATP is used mostly, 95% of it is used for muscle contraction, which we'll talk about later. So the main systems are glycolysis, citric acid cycle, and fatty acid metabolism. In glycolysis, we have glucose coming in, and just a quick reminder, because you guys already know this from your last test, but you get out 2 ATP, 2 NADH, and 2 pyruvate. And that pyruvate can go in 2 different directions. It could be converted to acetyl-CoA, or it can be converted to lactate. So when it's converted to acetyl-CoA, then it goes into the citric acid cycle. So for every 1 glucose molecule, we get 2 acetyl-CoAs because we had 2 pyruvates. It's just good to remember these numbers. He could always ask you anything about the number of ATP you get out for citric acid cycle, glycolysis, and a combination of the two. So in the citric acid cycle, these are the products that you get out. You have 3 NADH, 2 CO2, 1 FADH2, and 1 GTP, which is equivalent to an ATP. So if I were you guys, I would go back through the citric acid cycle, look at where each of these products come from and what's happening at that point, and just focus on those sections of citric acid cycle. It would be great if you also just had it memorized and could write it down before the exam, but if not, just focus on these important parts where the products come out, if that makes any sense. So then fatty acid metabolism, you break down a fatty acid through lipase, and it will be broken down also through beta oxidation. It gives you these products, and all of these products from glycolysis, from citric acid cycle, from fatty acid metabolism, they all go into the electron transport chain, which he talked a lot about pretty recently for this test. So you're gonna have 3 ATP coming out for every 1 NADH that you put into the electron transport chain. And this is because NADH, it enters the electron transport chain earlier than FADH2 does. So it has more potential to give energy and to make this system work, because this works like a machine. It uses mechanical energy and chemical energy to create ATP through ATP synthase, which is right over here. Yeah, so NADH will enter the picture right here in complex 1. It helps, its electrons are transported through each of these complexes, and protons are pumped through almost all of these complexes. Complex 2 does not pump protons, remember that. That's something that's unique about it. And then FADH2 enters later, enters into complex 2, but same thing. The whole purpose of this electron transport chain is to create a proton gradient so that in the end, these protons are being pushed through the last part of ATP synthase, which gives this whole machine energy. It gives it energy to push an inorganic phosphate and an ADP together to give you ATP. So that's just a really brief overview. Hopefully it helps you get a little bit bigger picture and to understand this whole process a little bit better. So with the big picture, I also wanted to mention, with metabolism, proteins, you use protease to break up proteins. The biggest proteases that you talked about were trypsin and chymotrypsin. And serine proteases are used in the catalytic triad. So just go over that mechanism and remember, just try to remember it. There's nothing too deep about that though that you should be worried about. So just make sure that you know those mechanisms and you know which enzymes are being used. And then for fatty acid metabolism, it's lipases. For glucose, it's glycosidases. and that's breaking polysaccharides into monosaccharides. This is, again, another review just of how your sugars cannot be digested if they're polysaccharides. They can only be digested if they're monosaccharides. Okay, so moving on from the bigger picture into, we're going to talk about muscle contraction. So I drew this little thing for you guys. It's a little bit, okay. So the two main players in muscle contraction that he talked about are actin and myosin. Myosin is the thick filament, actin is a thin filament. And they work together to shorten your muscle to contract it. So how this happens on the smaller, I guess, more molecular level is that neurotransmitters are released into the synapse. They bond into the bonding site of another neuron, and it sends a signal to the muscles that it can contract. So when the signal is sent, then the actin and myosin, this is where they come into play. So myosin has these cute little heads on it, and the heads, their purpose is to grab, I just imagine them grabbing onto actin and pulling it in towards each other. So that's contraction. And this is also powered by ATP. You know how I said 95% of the ATP in your body is used for muscle contraction? That's because this is happening all the time. This happens when you don't even think about it, when you're breathing. Anyways, so the myosin uses ATP, it attaches to the actin, and then when it releases an inorganic phosphate and an ADP. And then this cycle just continues as they move together and then relaxes as they move away. Acetylcholine hydrolyzes via acetylcholine esterase, which keeps this whole system running. If that was blocked, I think Dr. Savage talked about this with you guys, if that system was blocked, then that can be used as like a bioweapon to keep your muscles contracted and stiff, and it can be very dangerous. So yeah, we're grateful for acetylcholine esterase. Okay, then really quickly, the amino acids. Hopefully you have these memorized by now. I just want to go over really quickly, just you guys should know the pKa's, especially of histidine. Where is it? Histidine. So the pKa of that nitrogen is 6.2. And then the pKa of all of these amine groups and carboxylic acids, it's different. It's 9.5 and it's 2.2. So I'm pretty sure he will probably ask you a question about that will involve something about the pKa's. So remember those pKa's and remember what they will be like in different pHs. And also keep in mind which ones are hydrophobic, which ones are hydrophilic, and which ones have charges. So my advice would be to write out all of the amino acids when you get to the test. Do the best you can. Remember the one-letter codes and how to write them. You don't have to worry about the name. And that will help you a lot, hopefully, to answer some of the questions about charged ones or hydrophobic amino acids. So amino acids can be put together in different formations. I just wanted to talk about alpha helixes and beta sheets or beta turns really quickly. The thing that helped me most is just to remember that alpha helixes, they have 13 atoms in their little turn, I guess is what you could say. So sometimes he'll give you a question where you have to look at it and determine if it's alpha helix or beta sheet. And the best thing to do at that point is just to count the different atoms that are involved in the turn. So hopefully that makes sense. Maybe I can show you an example of what I'm talking about. Okay, yeah. Here's an example of a beta turn that I just drew. And to count each of these, I always start at the hydrogen bond because that's where he's talking about the beta turn starts. So I would count the hydrogen 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that has 10 atoms in it in the turn. So this is for sure a beta turn. Okay, so these are the secondary structures that I'm talking about, beta sheets and alpha helixes. And so that's important to remember and be able to distinguish between the two. Lastly, I'm going to talk about transamination. Transamination is the process by which these 3 amino acids get converted into these really useful molecules. So amino acid A gets converted into pyruvate, D into oxaloacetate, and E into alpha-ketoglutarate. So basically that's all you need to know. You know that this amine group will change into a carboxylic acid, and that's just what happens. That's the pattern. He said you don't need to know the mechanism, just to know that this occurs. And so which amino acid will turn into which one of these. And so this is another reason why drawing out the amino acids could be useful, because if you have these written out, you can count the carbons, and you can pretty easily distinguish which one's going to be pyruvate, oxaloacetate, and alpha-ketoglutarate. So hopefully that will be helpful to you guys. Oh, and I did want to make one more note about ketosis. So ketosis is the process of your body breaking down molecules into ketones, and those ketones are special. He talked about how they can cross through the blood-brain barrier. And so that's why when you're fasting, the ketones in your body are used to keep powering your brain, because that's one of the most important organs to keep alive. So the ketones will enter into your brain through the blood-brain barrier, and oftentimes you can also smell the ketones on your breath. So that's why your breath smells bad when you're fasting. Okay, I think that's about it. I'll make another video if I remember things, but hopefully this was helpful. And you guys will all do great on the exam tomorrow. Let me know if you have any other questions. Yes, and you got this. Okay, bye.